inequalities. And notice we're going to give our answers as inequalities, in other words, set builder notation, and also in interval notation. So let's look at the first problem, and what we're given is that this absolute value is greater than 4. Let's remember that an absolute value actually tells you the distance something is from 0. So absolute value turns everything into positive, whether the inside value was -4 or +4. So what we have to do here is account for both possible scenarios. So as long as our absolute value is isolated, which it is, we can split this equation into the two possible cases. The first one is the positive case. We keep everything inside the absolute value as it is, and then we just keep the outside as it is as well. For the second case, we keep the inside of the absolute value bars the same, 3x minus 2, but we change the inequality symbol and the sign of the 4, so it becomes less than -4. And we solve both of these problems. So we add 2, giving us 6, divide by 3, we wind up with x is greater than 2. Okay, so there's one solution. And for this one, if we add 2, we get -2. Divide by 3, we get x is less than -2/3. And there's the other part of our solution. Okay, so these are the two solutions. And what we're going to do in set builder notation is we're going to show what they are in unison together. So we will say that the values go from -infinity to -2/3. And notice we're not including 2/3 because the inequality symbol just says greater than, not greater than, or equal to. So we put the parenthesis, union, and then from 2 to infinity, right? All the numbers that are 2 or bigger than, not 2, but bigger than 2. And that's our solution written in interval notation, which we've all learned. So the second problem is very much the same. Okay, again, our absolute value is isolated. And just so you know, in case there happened to be like a 3 times, maybe this said 3 times the absolute value is less than 1, you would have to move that 3 over. So that's what I mean when I'm saying it has to be isolated. In this particular case, it's already isolated, so we can jump right into our two cases. So remember, the first case, you keep what's inside and you basically keep what's outside. You just lose the absolute value symbols. The second scenario, the negative case, you keep what's inside the absolute value symbols, change the inequality, change the sign of the number out here. And now we solve. So we're going to subtract 2 from each side, giving us -x is less than -1. We'll divide by -1, and I know you remember you have to switch that inequality symbol. So x is bigger than 1. And the negative case, we subtract 2, we get -x is greater than -3. Divide by -1 on each side, we'd get x is less than 3. And if you notice, this is a compound inequality where x is bigger than 1 and x is less than 3, so we like to write that x falls between 1 and 3. That's really the compound way to write this. And as an interval notation, we would say x falls between 1 and 3 with those parentheses right there. So hopefully you remember that. Okay, a little bit tougher is when we have rational inequalities. And rational, ratio means fraction, so we're dealing with inequalities that have a fraction. So the first thing we have to do is we have to look at our denominator and figure out which values should be excluded from our domain. If we look at this denominator, x plus 2 cannot equal 0. So x plus 2 cannot equal 0. So x cannot equal -2. That will result in an open circle on our number line when we go ahead and solve this. So now we kind of save that for later. So now what we do is we look at our inequality. It's already set greater than or equal to 0, and we kind of pretend for a little moment that this is an equal sign, and we solve. So if I was solving this, I might say, oh, I'm going to cross multiply by x plus 2, or I might say, oh, I'm going to multiply each side by x plus 2. Either way, we wind up with x plus 1 equals 0. And we solve it as if it's an equation. Oh, I'm sorry, x minus 1. Let's erase that. Okay. So x minus 1 equals 0, and then add the 1 to each side, and x equals 1. So it's a little pretty simple solving right there. But we actually want to go back here and see that it did say that we had an inequality symbol that includes equal to. That's going to be important because right now when we make our number line, over here at 1, x can be 1. So that's going to be a closed circle showing that 1 is included in our solution. Whereas at -2, we had an open circle because x cannot be -2. So at this point, what we need to do is we need to check each region on our number line. So in other words, we have to check a number to the left of -2. We have to check a number between -2 and 1, and then we have to check a number between 1 and infinity. And what I would do is I would just look here. I would say maybe -3 is the number I'll choose. -3 minus 1 is a negative. -3 plus 2 is a negative, and a negative divided by a negative is a positive. And look what we're looking for. We're looking for this fraction to be bigger than 0. So this would be part of our solution. So I'm going to start writing this out. So that means part of the solution is from -infinity to -2, not including -2. And now we'll check a number between -2 and 1 and see if we get a true or a false statement, see if it's bigger than 0. So I'm going to drop in 0. 0 minus 1 is a negative. 0 plus 2 is a positive. A negative divided by a positive is negative. And of course, a negative number is not bigger than 0. So this is not part of the solution. That's a big NO right there. And now we'll check a number bigger than 1. So I'm just going to use 2. That's easy. 2 minus 1 is a positive. 2 plus 2 is a positive. And of course, a positive divided by a positive is a positive. So all of the numbers bigger than 1 and including 1 are part of the solution. So in interval notation, we put a bracket with the 1 to infinity, and of course a parenthesis around the infinity, as we always do. So that one was really nice because we already had 0 on one side of the equation. Okay, on the next problem, we're going to have to get it so we have a 0 on one side of the equation. But again, before we do that, I always just like to look at the denominator and say x plus 1 cannot equal 0. Therefore, x cannot equal -1. I'm going to save that tucked away for later. That'll go on our number line again as an open circle. So what I would do at this point is I would probably subtract that 1 to the left side of the equation. I'm just going to do this and make it less than 0. And what we need to do right now is we need to be able to combine all of what we have on the left side into one big fraction. So what we would probably do, we want to get this common denominator, so we're going to multiply this by x plus 1 over x plus 1. What that gives us is one fraction on the left side with a denominator of x plus 1. So we have x minus 4, and we will need to distribute this -1 in. So we'll have minus x minus 1 is less than 0. And of course, we're going to clean this up, and you might notice right off the bat, hey, look at these x's. They cancel each other out. That's okay. That won't always happen, but that happens right now. And so what we get is negative 5 over x plus 1 is less than 0. And if we pretended like we did in the previous problem that this was an equal sign and we solved, we would just get negative 5 equals 0, which of course is not true. So we don't get another significant point on our number line. The only significant point we got was x cannot be negative 1. Sometimes we get multiple points on our number line that are significant. This time we just got negative 1. And of course, an open circle. So what we can do is we can go back to this equation right here, which really cleaned up. We'd probably want to go to this equation. And we'll drop a number in to the left of negative 1, in other words, less than negative 1, and see if we get a true statement. We'll drop a number in that's greater than negative 1, and we'll see where we get the true statement that x has to, or the left side has to be less than 0. So I'm going to take negative 2. That would give me negative 5 over negative 1, which is a positive. Well, positive is not less than 0, so that is not part of our solution. And now we'll test to the right. I'm just going to drop 0 in. Negative 5 over positive 1 is a negative, and that's what we were looking for. We were looking for numbers that were less than 0. So all of these numbers are less than 0. So our solution, if we wrote it out in Set Builder, would look like this. X is greater than negative 1. Of course, in interval notation, it would go from negative 1 to infinity. And I did graph this, and I thought you might want to know what it looks like. If this was our graph, we would have an asymptote here at negative 1, and this branch of the graph was less than 0. This branch of the graph looked like this, greater than 0. Okay, so that's what that one looked like. Sometimes helpful to get a visual on it. Okay, so number 3 is very much like number 2. So what I'd like for you to do is pause the video and give it a try. Okay, first you're going to identify what x cannot be based on the denominator. Then you will move the 2 over, get a common denominator so you can give yourself one fraction on the left, solve it as if it was an equation, and then test your values. Okay, so go ahead and pause the video. Good luck. Okay, let's see how you did. So hopefully you moved that 2 over, you did the distribution, and you consolidated everything on the left side. We pretend it's an equal sign, so we either cross multiply or multiply by x minus 5, whatever you like to think of, and then solved and got 13 as our significant value on our number line. And when you test these values, I would have tested right here, okay, and we're looking for numbers that are bigger than 0. And I found that the numbers between 5 and 13, if we drop them in here, they would give us a number bigger than 0. Okay, so let's just check it. If we put, say, 6 here, we would have had negative 6 plus 13 equals 7. 6 minus 5 equals 1. So 7 divided by 1, of course, is positive. So that's just one number that you could have dropped in there. Okay, so number 4 probably looks a little more complicated because it is, but there's nothing in here that you don't know how to do. So the first thing, as we know, x plus 3 cannot equal 0, so x cannot equal negative 3. And what we're going to have to do with our numerator is we're going to have to try to factor it. So we already have the 3x on the outside. It's almost like they pulled the GCF out for us. But when we go ahead and factor this, hopefully you get x minus 2 and x plus 1. Of course, that's all over the whole denominator, which we're about to multiply away, but I'm still going to put it. Okay, so now we'll multiply away the denominator, pretending there's an equal sign, and we will get 3x times x minus 2 times x plus 1 equals 0. You should remember how to do this, right? Zero product property basically says that for these values to multiply to equal 0, x must be 0, 2, or negative 1. Those are 3 significant points on our number line. Go ahead and check them on the number line and see if you can come up with the right solution. Pause the video. Okay, so hopefully you got the same regions as me. So from negative 1 to 0 and from 2 to infinity. Okay, I thought the easiest spot to put this was here. We can't use the one when we've lost our denominator, so we can't use this. But what was nice about this one is when you square anything, it's positive. So we really could look at the numerator and know that the denominator, no matter what, was going to be positive. So for example, I took negative 4. Substitute a negative 4 in here. It's a negative times another negative from the middle binomial times another negative from the third binomial over a positive wound up being a negative number. Okay, so that's kind of how I did that. Hopefully you did as well.